Bismillahirrahmanirrahim. In this video, I'm going to talk about two-part K Factorial Design of Experiments. So this two-part K Factorial Design of Experiment means that we are going to conduct such an experiment which have K number of factors and every factors have only two levels. So this type of design of experiment generally used to screen the different types of factors. So screening means what? Screening means, let's say we have 10 different factors that are affecting our response variable. So as we know that in a design of experiment, that is basically the study of identifying the relationship with the dependent variable with the independent variable. So X are representing the factors, Y are representing the response variable. So that these are indicating with respect to the K. So let's say we have the 10 factors and every factor has two levels, and we want to identify out of those 10 factors what are the factors which are significantly affecting the Y variable. So that means we want to identify from the 10, it might be possible all 10 are significantly affecting the Y, or it might be possible out of 10 there are 3 or 4 factors that are significantly affecting. So the remaining 5 or 6 or 7 factors, we can remove that. So this is called as a screening process. So that means we want to identify what are those factors which are actually affecting the response variable. Okay, so two-part K design of experiment generally using for screening purpose or for the factors, as well as you can also use as a general experiment purpose as well. But generally people are trying to prefer the general full factorial design of experiment, because in that particular design of experiment you can take for every factor as many levels as you want. But in two-part K, so every factor has only 2 levels. So when we are talking about two-part K, so that means the minimum number of factors could be 2, or it could be number of factors more than 2. So for that, there are two main concepts that in which we are interested, because due to the two factors, so if we are talking about with respect to analysis of variance perspective, if we want to apply the analysis of variance, so that means due to two factors, we have to apply the two-way ANOVA methodology, right? As the number of factors are increasing, like if there are 3 factors or 4 factors, so that means the number your methodology will be changed from two-way to factorial analysis of variance. Okay, so we can also convert this two-way ANOVA equations into the regression equation. How we can do that, we will discuss later while we were implementing this concept in Minitab. So right now, the important concept is when we are discussing that there is a 2-factor or more than 2 factors. So in two concepts, we are interested, either we are interested in the main effects as well as the interaction effects. So like, for example, if we have a 2-factor like factor A and factor B, and we have considered as a 2 levels, one is low, one is high, low and high for the factor B. And when we have conducted the experiment and having the factor A at low level, having the factor of B at a low level, so what's the output we are getting? Similarly, what's the output we are getting over here, and so on. So there is a 2-part, that means 4 results are possible. So this is a one-time replication. Okay, so now we want to find out what's the how A factor is affecting the response variable. So that is indicating when I am shifting from factor A from low to high, how much increase or how much decrease is possible in a response variable. Similarly, with respect to B, if I am moving from low to high, how much increase or decrease is possible in my response variable. So how we can calculate that? We can calculate that through main effects. So that is every factor's effect on the response variable. So for factor A, how we can calculate that? That one average at the high, that is 52 plus 40 divided by 2, and average at low, and we can subtract from the high to low, and this is indicating 21. So what does that mean? That is indicating that when the factor is moving from low to high, there is an increase in the response variable, that is 21 unit. Similarly, for factor B, we can calculate the main effect, that is average of this minus average of this. We can see that when we are shifting from low to high with respect to factor B, so there is an increase in a response variable for the 11 unit. Okay, next we are moving towards the interaction effect. Okay, so what does that mean? Interaction effect, how we can, first of all, how we can calculate the interaction effect? That is, we will firstly diagonally calculate the value. Misha, always we will calculate the average from, uh, you can say diagonally from left to right, and then this one, right? So that is 20 plus 52 divided by 2 minus 30 plus 40 divided by 2, we are getting the value of 1. So what does that mean? That is indicating that when we are at a factor A and the difference between in factor B between low to high is increasing when we are shifting from factor low A to low to high, okay, and then this difference is increased by 1 unit. Okay, so that is basically the main effect as well as the interaction effect. So that is indicating, so as the number of factors are start increasing, so their interaction is very important. So right now we have just considered a very simple example, that is with respect to the 2 factors. Okay, so if there is a 3 factors, so then there would be individual factors effect, that is called as the main effects, and there is an interaction effect with respect to two factors as well as all 3 factors. So as the number of factors start increasing, so we have to find out the interaction effect with respect to 2 factors interaction as well as 3 and so on. Okay, so let's do, we should implement this 2 power k in a Minitab. So how we can do that? The example I am going to take it, 2 examples I am going to discuss in this video. So number 1 is, that is this experiment, that is basically 2 power 2 design of experiment, and I am going to take it as a full factorial design of experiment. So the experiment in which we are going to conduct is, the response variables are the defects per unit. Okay, so we are noting down that how much defects are occurring on each unit, and the factors we have taken as a time and the pressure from our production processes. And we want to see that if, and we have also done some, you can say brainstorming, and decided that what's the low value of the time, what's the high value of the time. So the 2 level we have decided for the time factor is, low value is 170 and high value is 190, as we have discussed that 2 power k. So k is a factor that is a time, and 2 is a level on a bottom side, that is basically the low and high values. So means level 1 is, and what would be the defect when we have the time 170, what would be the defect when we have 190 time. Similarly, we have considered the second factor, pressure, and the first level is 95 and the high level is 105. Based on that, we will design using Minitab, and I have repeated this experiment 3 times. How you can design design of experiment using Minitab, because that is a best practice. First, we should design that design of experiment using the software Minitab, and then we should implement practically. So means to analyze this design of experiment. So first we are going to design the design of experiment, which is 2 power k. That how we can do that? We should go to stats, DOE. Okay, so there is a different type of design of experiment. So right now I'm going to conduct factorial, then create. Okay, so there is a different type of design of experiment. So I'm going to take the first one, which is 2 level factorial, and the number of factors are 2, which is time and pressure. Then we will click on design. Okay, so here this is indicating how many time you want to repeat this experiment. So I am saying 3 times. Press OK. Then they are asking about the factors. So the first factor we have, that is the time, and the second factor we have, that is the pressure. Okay, so type I am going to write now taken as a text because I have considered as a factor. So I don't want to take it as a numerical perspective. So the level is, because only 2 level, one is the times lower level is 170. Okay, or you can say hours or minutes, whatever the unit is. So high is 190, pressure low is 95, high is 105. So press OK. And then in an option, if you want that your design of experiment should be in a random order, then you must click over here. If you don't want that your design of experiment are in a random order, it should be in a sequence, then uncheck this one. So I am going to uncheck this one right now. So press OK. And then this is okay, the default option, so press OK. So this is basically what we have done. We have designed a 2 power k design of experiment. Okay, and this is indicating full factorial. Okay, full factorials means that is 2 power 2 is the 4 number of experiments multiplied by, because we are repeating this experiment 3 times. So that's why we have the total 12 number of experiments. Okay, so 2 factors, right? So 2 power 2, that means 4 would be the single time repetitions 4, because we are repeating 3 times, so the number of experiments are 12. Okay, so the next thing is here on a bottom we can see that that the standard order, random order, because we have unchecked the random order, that's why the standard order as well as the run order are the same. If you check that one, this would be the different. Okay, so this is the time, this is the pressure, right? And blocking concept is used when you are considering as a particular factor as a noise factor, means that is the separate thing we will discuss later. Right now there is a 2 factors, and the output is basically that is a defect per unit. Okay, so that means now we are going to perform the design of experiment, and we want to see that if the time is 170, the pressure is 95. If we set this levels, then what's the defect per unit? So I have conducted the experiment and I have found these results. So I have done already this thing. So when our time is 170, our pressure is 95. So what's the defect per unit? So I have completed this experiment. Now I want to analyze this. So in order to do that, we should go to Stat, DOE, Factorial, and then Analyze Factorial Design of Experiments. So Analyze Factorial. So we need to send response variable. So double click on that one. Click on terms. Okay, so terms we can see all those factors, which are 2, as well as AB means that is an interaction effect. So press OK. On a graph, we want to see the Pareto effect plot as well as normal effect plot. And this is to check the property of the two-way ANOVA. Okay, so that you might know after fitting the ANOVA that it should be fulfill the properties of the residue. So what was that we will see in the results. Okay, in a display we are saying only show the models and not show us those factors which are not significant. So press OK, and in a result, okay, press OK. Okay, so after clicking, so what we are getting that first of all we are getting on an output that is called as the coded coefficients. Okay, So this first thing is like right now we are getting the p-value against time factor, we are getting the p-value against pressure factor, as well as we are getting the p-value against time, and that is an interaction. So here what we can see that the p-value is less than your alpha value, which is 0.05 I have considered. So it's up to you, either you can take it as a 0.1 or 0.5. So if I'm taking the alpha value 0.05, that means whatever the decision I have taken, that is, I'm 95% confident about those decisions. So that means there is a 5% error in my decision. So right now, because the p-value is less than 5%, so I can say that time is significantly affecting my response variable. So that means if I change the time, it will affect on defects per unit. So by changing the time from low to high or high to low, so there will be a significant effect on defects per unit. Similarly, pressure is also a significant factor, as well as interaction is also a significant factor. So all three are the could be considered as a model term. Okay, so these two things are important in order to predict. Like if I change the time from 170 to 200 or 190 to 200, so what would be the defect per unit? Okay, so how we can do that, I will show you later. But right now, the relationship between effect and coefficient is that this is the constant term, because this is using to write down the multiple regression equation. So this is a value, that is a constant factor. This is B1 value, this coefficient 3.51. X1, that is indicating the first factor, which is time. Then B2, X2, that is indicating the second factor, which is pressure. Third, B3, X3, that is indicating basically the interaction, which is time and pressure. So basically this is under the coefficient column, this is basically your multiple regression line. Okay, so which we can use to predict what is the value of the time we should take, what is the level of pressure we should take, and what would be the value of defect per unit, which is our response variable. And the relationship between the coefficient and the effect is, if we divide the effect divided by 2, we will get the corresponding coefficients, right? And next, in the end, VIF stands for variance inflation factor. This is basically used when we have the multiple factors. So we need to check whether is there any multipolarity or not. So the idea is, if the variance inflation factor is 1, that is the best value, or you can say near to 1, then we can say we are in a good shape. That means there is no multipolarity exists in the model. Multipolarity means there is no relationship between time and pressure. So they are independent variables, right? If the variance inflation factor is 1 to 5, mostly statisticians says that they have the moderate multipolarity exist. That can also be in some case acceptable, but if there is a variance inflation factor is more than 5, some says more than 10, that is not acceptable. Okay, but right now we are in a very good shape. Okay, next thing is they are indicating the R square and adjusted R square, that is basically indicating the model fitness. So right now this 91.55 or 88.39 indicate that. So basically 91.5 1.55 means that time and pressure at their interaction. So these two factors are able to tell the variation in the response variable, which is defect per unit, 91.55%. So due to these two factors, 91.55 variations that are occurring in defect per unit are time and pressure. But the rest of the variation we don't know. That is basically called as the error. So that means we can say that defect per unit okay, that is a dependent variable, would be equal to, so this is our response variable y, and our regression equation would be 7.083 plus we have 3.583 is the coefficient against time, plus 1.250 has the pressure, plus 1.50 has time and pressures interaction. So all have the positive coefficient, that is indicating they have the positive effect. If we start increasing the time from 170 to 190 to 200, so right now this is indicating they have the positive effect. Okay, so that means to increase the time, the defect rate will be start increasing. They have the positive effect. Similarly, pressure is also have a positive effect. If we increase the pressure, it will start increasing the defect per unit. Similarly, in traction, if their value is increasing, okay, so it has a positive effect on the defect per unit, right? Okay, so the next is that is analysis of variance. Basically, again, if you can see the p-value of against each single factor, that would be the same. By the way, right now this is indicating, is this ANOVA model is a best model for this data set? Yes, this is a good model because right now we can see that this p-value is indicating with respect against the model, which is less than 5%. So we can say that we can rely on this model. And what is a model? The model is that is this one. Okay, as we have written down upper side earlier, that is defect per unit is a response variable. This is a constant. This is time, pressure, and interaction. So based on that, we can predict defect per unit while putting the value of time, pressure, and the interaction. Okay, similarly, we will get some plots that is normal probability plot. Okay, so this here we will see different type of symbols. Right now, the maroon color is indicating that all the factors that have the maroon color, they are significant. So that means factor A also significant, B also significant, as well as interaction. Similarly, we can see from the Pareto chart that AB as well as B are significantly affecting. So here we can also see that the most significant factor is A, then AB, and then in that B. So it is also prioritizing, but all three factors are affecting the defect per unit. And in the end, this is basically post-model property that residual must be normally distributed, so it look like normal because all the blue dots are lying on the ideal normal probability plot, which is a maroon color. Okay, so here we cannot see any trend. So this is also the homogeneity of the variance, right? As well as that is normal. So all things are good. I hope you understand this one. So let's draw the mean effect plot as well as the interaction effect plot. So how you can do that? You can do that with factorial plots. Okay, so just on a graph, that's okay. Press OK. So this is mean effect. So in a mean effect, how you can see interpret this one, as we are moving from low to high in a time factor. Okay, if this line is, as long as this line is more diagonal, like which is right now is indicating, then this is a significant factor, which means moving from time 170 to 190, so defect per unit is significantly increasing. Similarly, pressure is also showing that when it is moving from time 95 to 105, it is significantly affecting. If this line is on a horizontal form, okay, so that is indicating that this factor will not affect while we are shifting from low to high or high to low. Okay, but because right now this is in a diagonal form, that is indicating that this factor is significantly affecting. Similarly, in interaction, because these two lines are interacting, cutting each other, okay, or you can say interact with each other, so that's why these two factors are affecting our response variable. But in order only relying on this these graphs, instead of relying on these graphs, you should rely on the plots. Sorry, on ANOVA results, which we have discussed earlier. So there is another option in Minitab that we can optimize our factors as well. Okay, how you can optimize that? That is basically response optimizer. If I click over here, okay, and what I want to do, my target is I want that there should be minimum number of defects per unit. Okay, so that's where we have set the goal. On a setup, they are indicating what is a goal, right? And what's your target. So this is by default, they have considered there's a minimum number of defect. They have targeting 1. The maximum data value is 15 in your data sets. So that's when you are selecting on that one. Okay, on an option, you can set a particular constraint. Like for example, on your process, you are saying that you should, instead of holding 170, which is a lower value, you should hold it 190. So you can do that. So right now, but what I am doing that I am saying there is no constraint. So if there is a constraint, so you can put over here. Okay, so we are using 95% confidence, and the confidence interval we are taking two-sided. So press OK. The rest is okay. Okay, that's fine. So press OK. So what we are going to get, so this is the parameter which we have set. Okay, and the important thing over here is that is this one, this graph. You can say that if I double click over here, okay, what I found that that is this one, this current line. So they are saying that if the time is 170 and the pressure is 105, if you use this setting, the optimum value which we are getting, that is 3 defects per unit we will get. And this is the ideal condition with these setting, okay, with low or high. So you can also check that if I change this, like this is right now time, if I change from low to high, so you can see that our defect rate is start increasing. Okay, if it is again, that is 3. Similarly, if I change the pressure from high to low, it is again not 3, it is 4. So that means this is the best ideal condition, or the optimum value is if we set the time 170, if we set the pressure 105, the defect per unit would be 3. Now we can also predict. So if I click over here, I will get the results, that is this one. So the fit value is basically, that is the defect per unit would be 3 at 95% confidence interval, mean 5%. So that means we are 95% confident that the predicted value will lie within this range. Okay, so the defect per unit will lie within this particular range. Okay, I hope you understand this one. So in this video, I am going to discuss I have discussed part 2. So to part 3, we will discuss in the coming video. Thank you so much.